Hello everyone, I am Srimanti and I am currently working as an ML engineer. Okay, so we are going to discuss an extremely important ML algorithm which is decision trees. So the name itself suggests the kind of algorithm and the kind of dataset that we are going to deal with here, right? So the decision tree is actually arguably the most powerful ML algorithm that is out there that can fit a complex dataset, and also it is like very important for your ML career and understanding. So you have to listen carefully, and if you follow this video till the end, I can guarantee that you will be able to understand all decision tree questions. You will be able to solve all of them in college, exam, in gate exam, everywhere, in interviews, and you will be able to master this concept perfectly. So what do we mean by hypothesis space? It is the sample space of all the data points that we are going to use in this model. And so our hypothesis space here in this case is going to be a tree. Big deal. So, okay, so now that we have this, let's take and let's consider a sample data set to understand the concept more clearly and more thoroughly. Okay, so so what we are going to do here is that we are going to consider a data set of flowers, and there's going to be three kinds of flowers, and they are going to be decided based on like two features. We are going to keep it very simple so that you understand the basic idea. So there are two features that we are going to consider. One is petal length and petal width, and based on these two features, we are going to divide our data set into three classes. Okay. Let me show what I'm trying to say. So suppose this is our first node. Total sample points that we have is 150. That is the total number of data points in our data set. In the beginning, at the current moment, the total points is 150. So this is the first node in our tree. So you know, like a tree, what it looks like. This is a tree, right? So this is our first node in this tree, arguably this node. So we have total samples as 150. So now this one would have petal length, let's say that is less than equal to 5 centimeter. So what do we mean by that? So we are going to have like, let's say the total length in our data set, petal length, it varies from 0.5 centimeter to 10 centimeter. So 5 would be an appropriate middle ground. So let's say around 50 points have petal length less than 5 centimeters. So that is going to be yes. So this is the question that we ask at this node. Is the petal length less than equal to 5 centimeter? Yes. Then we go here. This means that this has sample data points 50, let's say. And the class, like whenever the petal length is less than equal 5 centimeter, we don't need any other features. We can directly say the class is going to be x1. Here, all the points, 50 points, they have class x1. So remember, this is not the real life. This is basically a sample scenario, a very dumbed down scenario that I'm using so that you get the basic point of decision trees. So this is the, at first node, you ask a question. Is the petal length less than equal 5 centimeter? Yes. Then you go here and you have total 50 samples out of 150. So the rest 100 samples have petal length which is greater than 5 centimeters. This says class x1, some class. Now let's say no. So we know now this has 100 samples. So now, and 100 samples, and we have two classes here. Some are x2, some are x3. Based on this, x1 class, x2 class, and x3 class. So basically here we would have, let's say, now the next question we are going to ask here, because we have not reached a single class at this node. So next question we are going to ask is this less than equal 5 centimeter? So we know the sample here, total samples is 100. Great. So now that we are going to ask this question here, this is going to be yes for some and no for the rest. So this is going to be again a leaf node because now we have class x2 only equal to x2. So this one, let's say this has 45 samples. So 45 total samples in our dataset has class equal x2 and it has petal length less than 5 centimeter, sorry, petal width less than 5 centimeter and petal length greater than 5 centimeter. We have this. We have 50 samples in our dataset of class X1 having petal length less than 5 centimeter and some wide variation of petal width which we don't care. Because petal length less than 5 centimeter means 50 class samples from our dataset that our model will learn. And no. Well, how many are left? 55. So this is going to have 55 samples. This is 55. And class is going to be X3. Right? So this is class is going to be X3. Samples total is 100. Total 45 samples here, 55 samples here. And we have now got ourselves a decision tree proper implementation. Okay, so let's get acquainted with some terminology. So these three, this, and this. These three are the leaf nodes. What are they? These are the leaf nodes. A little bit of cursive. These are the leaf nodes, and these are the internal nodes. These are the internal nodes. So at each internal node, we split based on a particular attribute or a particular feature. And at leaf nodes, we have, we classify it as a particular class, and it is where our tree ends. Now, this is basically at training time, how we make our tree. So now the question is, what do we do at test time? Suppose we have a particular X here, as in we have a particular petal length, we have a particular petal width. Now, what do we want to do? We want to find out which class it belongs to. It's very simple. I think you can all guess it. It's OH only. Yeah, sorry. So basically, you can use this to think about it. So OH, H is the height of the tree. So at each node, we know whether it's yes or no. So we don't need to explore the entire tree. We will go down perfectly the height of the tree, and then we'll be able to reach either of the leaf node. So let's say we have something like a petal length is 2.5 centimeters. So then yes, and we have class X1. The petal length is let's say 5.5 centimeters. Then we know it's going to be no. Then we are going to ask ourselves, we have it in the data set, petal width is 2.5 centimeters. Then we know it's going to be X2. If petal width is 5.5 centimeter, we know it's going to be X3. Very simple, easy peasy. Okay, so now that we have this, let's try to dig a little deeper. Okay, so this is a very, very easy example, but let's try to take another example, and we'll try to bring out the maths based on that example. Okay, so now that was a very, very basic example. Let's take another example to understand it very clearly, even more clearly. So let's classify based on like humidity and precipitation. We will also see the graphs here. So focus carefully. So this one is humidity. So now you know less than 50% or greater than 50%. So if it's less than 50%, question mark. So that means, let's say yes. So it means it's not that much humid. So it's going to be sunny. The class is sunny. We can also write this class, denote this class as 0. Okay, let's go with that. Now you know, so I'm going a little bit faster here. So no means the next feature will come here. Precipitation. Is it less than 50%? Okay, the handwriting is going a bit bad. So yeah, I mean, you can understand this. This is precipitation less than 50%. So this is going to be, let's say yes. Then what do we have here? Humidity less than 50%. Precipitation also less than 50%. So means cloudy. Let's say this class is 1. We are denoting the class as 1. And now let's say no, which means it's going to be rainy. Which means this is higher than 50% precipitation, greater than 50% humidity. Okay, so one thing I mentioned, so this cloudy means greater than 50% humidity, less than 50% precipitation, going to be cloudy. If it's greater than 50% humidity, but greater than 50% precipitation, it means rainy. So we are denoting this class as 2. This is another simple example. I hope you get this. This is very easy to understand. Now that we are done with this, so now basically these classes 0, 1 and 2, these are like our y or the target variable, right? So we don't generally represent this as 0, 1 and 2. Instead, we use our binary representation. So it's called one-hot encoding. So what do I mean by that? So basically 0 would be represented as 0, 0. 1 would be represented as 0, 1. 2 would be represented as 1, 0. So where am I getting this? This is the binary representation that we are using. And this is the one-hot encoding that we'll be using in our code to implement this, because it basically standardizes the things and it's easier to handle. Now, how did 2 get transformed into 10? So this is basically the binary representation. This is like very basic of CS. I think you know this, but still I'll just go over in brief, like in 2 to 3 seconds. So basically how we are getting this to this. So basically in binary, we have the base as 2. In decimal, this is decimal. In decimal, we have the base as 10. So when we want to transform decimal into binary, so what we're going to do is we're going to divide 2 with 2 because of the base. So it's going to be the remainder. This is 1 and the remainder is going to be 0. Again, we divide 2 and we get the remainder as 1. So basically, this is how it goes. 1, 0 is our final answer. So regardless of whatever it is, basically you take the remainders together in the reverse order and then you have the binary representation. This is the binary representation or the one-hot encoding that we are talking about here. One-hot encoding. Let me just write that down. One-hot encoding. Great. So now we have this out of the way. Now I also want to discuss another important thing. Keeping in mind this graph. So basically these, as you know, I said these are the leaf nodes. Now it can happen, remember this very carefully, it can happen that even though humidity is less than 50%, still some point here is there that is like cloudy. It can happen, right? Humidity less than 50% doesn't always mean it's going to be sunny. So let's say this has total 49 samples and one sample is of cloudy here. So this one has one sample cloudy and 49 samples of sunny. So in this case, what we are going to do is that if we know that this is our final tree and we do not want to divide this any further, so then we know that this node is going to be sunny. So there is a very slight chance of this being cloudy when we are trying to, at the test time, when we are trying to decipher a particular point. So, but whenever we are classifying this node and we know that this is our leaf node, we are going to take the number of the class name of the one which has the larger number of samples. So this one we are going to classify it as sunny. We won't bother about cloudy at all unless we want to divide this further. So this is going to be sunny. Great. So now that we have this, it can happen. Like it is not necessary that all the points here will be of sunny. It can happen that it can have one as cloudy. So now that we have this, let's try to draw a graph to understand this even better. Cool. So now let's draw the graph. So we have only two features, so we can use a 2D graph here. So this is going to be, let's say this is precipitation and this is going to be humidity. So we have the first one, if you remember, it was humidity less than 50%. So this one, let's say, is 50% for humidity. This one is 50% for precipitation, right? So this one is 50%. So if humidity is less than 50%, regardless of precipitation, this entire thing is sunny or class 0, right? So this is very easy to understand. Less than 50% humidity, this line, this entire thing is sunny. Great. Now when humidity is greater than 50%, then precipitation comes into play. So this one, let me just remove this because this is not needed. This one is not needed. So we only need here this line. So if humidity is greater than 50% and precipitation is basically less than 50%, so this region, let's just draw this here. So what is this region? This region is going to be, this region is going to be cloudy. This class 1. And this region, just to denote them separately, this region is going to be rainy. So our class 2, right? So we have humidity. We have humidity and precipitation as two features. We have sunny, we have cloudy, we have rainy. So these, this and this, These are the decision boundaries that we are trying to find in our data set, in our model. Like, in classification, we have decision boundaries. So similarly, in here, in decision trees, we have these decision boundaries that we are trying to find. Okay, so there's now a fun fact time. So basically, decision trees do not require any kind of data preparation or any kind of feature scaling, nothing. It's very easy and very simple to use. So, I mean, this can be a popular interview problem. So remember that. It's very important. Remember this, but it's also a fun fact. Okay, so now that we know our target variable and the data set properly, and we have a good idea of what we're trying to solve, now the next thing that comes is how we can get the attribute we need to split at each step. So as you remember, first in my example was humidity, then it was precipitation. So that was just a random example, but we need to know which attribute. Suppose we have a lot of features and we need to know which feature we want to use at each step, right? That is very important. So now that, so we obviously can't have like a huge tree with like lots and lots of features, and like suppose we had used precipitation earlier, then we would have gotten a larger tree. We need to find the most optimal and the most shortest tree that we can use, and that would make our process faster. So that is why we are now going to understand the maths behind how we are going to decide which attribute to split at each step. Okay, so let's get into that. It's going to be a little involved. I'm warning you, so be very careful and listen carefully. Okay, so now we know that y is going to be our target variable. So y takes values from 0 to r minus 1. So when we have r total classes. In our example, r was 3. So now the formula that we are going to use here is this. So let's say like we have probability of y equal y. So what do I mean by this? So y is our target variable that we are using here. So y takes values from 0 to r minus 1, as I said. R minus 1 when we have total r classes. In our example, r was 3. So this is going to be the probability of how, our y variable is distributed over this. Now that we have this, so now we know this. So now the next thing that comes is h of y. So this is a very important term that we are going to use. This is entropy. Why we are doing that, I'll get to it in a bit. So h of y is probability of y equal y, this term that I just now mentioned. Now, very careful, listen. Log of probability of y equal y. So what is this? This is the surprise associated with all the data points. So why do we use this to represent the surprise? Because suppose if we had only one class, that is class 0, then probability y equals 0 would have been 1. So in that case, log of 1 would have been 0, which means there's no surprise. All the classes are 1, so we don't have any surprise. And log of this thing, it represents the number of bits that we are using in our representation. So that is why log is very important here. Let's try to see it in a different light so that we understand it better. This. Okay, so now we can also think of this in a different way. This is expectation of minus of log of probability y equal y. So expected value, this is basically our entropy is expected surprise. Why? Because this will be if we basically do this. Okay, one thing I forgot, summation over y. So this one would be summation over y, probability of y multiplied by the term. Log of p of y equal y. Yeah. So this is our entropy that we have here. This entropy is basically the term that we are going to use to determine which attribute we are going to split at each step. So why are we going to use this? Let me try to explain that. So entropy means the randomness or the chaos in a particular system. As you know, like Brownian motion, it was like full of very chaotic. So similar is here as well. So basically hy represents the entropy, which is the randomness. And we want our system to have zero entropy. We always want that. We always want a stable system. So that is why whenever in a particular node, now listen very carefully. So you remember this one was our decision tree as it was going. So this was the leaf node. In a leaf node, I said If you remember, I said that there could be that some small percentage of points that are of a different class, right? So we want this node to have all the classes of a single class variable, all the data points to have a single class here, right? Then we know for certain that whenever this attribute is going to be satisfied and we come to this node, we know that this node is going to be of that class with 100% certainty. 100% certainty means this set has entropy 0. Remember this. So basically what we want here is to minimize this entropy. But this has no x, that is no feature, so we don't know how to do this. So now comes in the conditional entropy based on the feature. It's interesting, right? It's getting interesting. Yeah. So now comes the conditional entropy based on the x, so which we'll use to determine our the feature that we are going to use to split at each step, so that we get to a tree that has the least entropy and is the most stable. It's very interesting. Please listen carefully. H of y given x. X is our feature. This is going to be simple. Y equal y given x equal x minus log of probability of y equal y given x equal x. Summation y. Perfect. So this is the conditional entropy. Conditional entropy. This is our conditional entropy that we are going to use always to determine which x to use at each step to split at each step. So this one we used humility. So in this node we are going to apply this formula h of y given x. X we are going to take in all the xj. So here we had two x. So basically it was humidity and precipitation. We would use humidity and try to find this out, and we would calculate this formula, this value. We would use the next one, which is our precipitation, and calculate this. Whichever has the minimum h, we are going to use that to classify based on our, we are going to use in that node to split the tree. Perfect. I think you get this. So this is very, very, very important. Now that we know this, our work is done, practically done. It's not even 95% or 98%, it's 100% done. So now it's time to write a short pseudocode so that you understand what I'm trying to say. And you can implement that in any language that you prefer. And you can try it out to see that it works. I can guarantee you it works. I'll also make a video showing the hands-on implementation. But if you want to do it right now, I'll share the pseudocode. Great. So now I'll share the pseudocode. So first thing is D, which is our data set. Xi, comma, yi, I equal 1 to m. Let's say we have m total data points. So this is our data set. Now let's say our class, our function name is learn tree D. So first thing, as you know, if we are writing a pseudocode, we'll have to get the edge cases out of the way. It's kind of a recursive one. Our tree is obviously recursive. So first thing, we need to get the edges out of the way, edge cases. If we have xi, comma yi belongs to D and yi equal to k. So for all I. So for all I, if we have at this node, whatever I we have, so for all I, it belongs to the data set, obviously. That's the known criteria. It belongs to our hypothesis space, as I said. And yi is k. That is, all of them belong to the same class. So now we know that this is an edge. So this is going to be a leaf node. So we know this is going to be a leaf node. So return new leaf. Okay. This is an edge case that we have. Get this out of the way. Now the next thing is xj. So basically xj, choose xj. How we are going to choose xj? Don't write choose in pseudocode, but xj is going to be such that minimum of h of y given x among all the features. As I just now said, the minimum entropy we are going to use to choose the xj. Now we have the rest of the tree. So the tree would be d of. Now we know the tree would be d of L such that it will have all those points xi, comma yi such that xi is s. So just now shows j. So this j is going to be this L that we are going to use here, and dl is our new tree. Let's give a comma here. This is going to be our new tree with the remaining with the attribute that we chose to split, and this is our tree. Okay, so now that we have done this, we know the tree that we are going to use based on the particular feature that we are going to split our tree. So basically now we are going to return. We're going to return based on the attribute that we just now decided and the rest of the tree. Perfect. Now we have this out of our way. This is just like recursive function. Base idea, I think you have got it. And it's very important to understand this so that you can implement this on your own very, very easily. And whenever you're using any kind of scikit-learn library as well, you know which hyperparameters to use. We know which loss we are using. This loss is very important, like very, very important. It's an extremely popular interview question. Cool. Fun fact time. So decision tree is actually a white box model because it's very easy to understand and we know exactly what is going in it. We can implement it from scratch. But in often other cases that, like, for example, I'm not going to mention the example. Think of that, which are the black box models that we don't know what is going inside. We just know the input. We don't know what's going inside, what formula, what recipe it's cooking up. And we just know the output, and we can change some parameters, true, but we don't know exactly what is going inside. It's not very intuitive. So think of such examples and then drop them in the comments. I'll check and see whether you're right or not. That's very, very important. Yeah, I think this concludes our understanding of decision tree. If you have come this far, if you have understood it, great. You deserve a round of applause. Amazing. So, and also, I can tell you that I'm really proud of you that you're following along all these playlists, understanding all the ML algorithms, because very soon, like, ML is going to be everywhere. It's already is spreading out. It's already in 50 to 60% of job spaces. So if you understand all these algorithms thoroughly, then you know that you're on the right path to your perfect job and the best job that's waiting for you. Just get a little bit of hands-on experience with these. Try to implement them, try to understand them, try to rewind it to understand it even more thoroughly. But if you are coming this, if you have come this far, new algorithms are waiting for you. And if you're understanding all this, then amazing. You are a genius. Great. So now, thank you. I hope this helped you. And yeah, let's see. Let's stay tuned for another time.